Hello and welcome to this video on day 4 of circle theorems. We will be discussing in this video some kind of various theorems that we have not talked about so far with circles and kind of hit some vocab you might be familiar with and then kind of move into some practice with each of them as we get forwards in this particular video. So now let's get into our first part. So in our first part, we see that we're talking about something called a circumscribed angle, which you can see I've underlined right there. It is basically an angle where you have a point on the outside and two tangent lines are two secant lines coming away from it. And it's kind of around the circle, just like a circumference is going around a circle too. So the couple things you need to know about circumscribed angles is that if you have point D in this example, and it is kind of tangent to the parts, so you can see how it makes an angle on the outside of the circle there. One thing you need to know, as you can see in these steps before, if we know angle Y is at angle A is equal to Y, and B and C are 90 degrees because they're tangent lines, you can figure out that angle Y, or angle A and angle D, are basically going to be supplementary to each other because they're what's left of 360 in this little quadrilateral shape from A, B, C, D there is basically just D and A are across from each other. And we already talked about in prior videos and lessons that quadrilaterals have opposite angles are supplementary for inside of circles. There are three scenarios where we could see some things like this being applied. So the first being basically looking at their arcs as well. So we have this point B in this first example where we are looking at one arc is from A to C, and you can kind of call that a minor arc because it's kind of the smaller way around. And then in blue, we have the what is called the major arc, the long way around. So you can figure out the angle we wanted in this scenario, which was angle B right there, is going to be equal to half of the difference between the long way around and the short way around. So pretty straightforward there. We just do 240 minus 120, and then you get 120. Half of that is 60. So angle B up there, angle ABC in red right there, is equal to 60. And that's the same thing for the next two examples where you have two secant lines and then a combination of tangent and secant line together. So in the middle example, you would have kind of the long way around would be that red arc, and then the short way around would be this arc from B to D. Half the difference would be equal to 35. And so you know that angle A up here is 35 degrees. And then finally, we have a similar thing going on where you have in green is that larger 164-degree angle. The small part is this 70 right here. So half the difference between 164 and 70 would be 1/2 times 94, which equals 47. And that means that this angle right there is 47. So those are all three scenarios you can see involving this one theorem involving circumscribed angles of various types. So we're going to work through three example problems using this theorem now. So to start off with example E, our part E of the first section of our notes, we have a 25-degree angle right there that is hitting arc AC in red right there. Since we know that 25 is an inscribed angle, that means that that arc right there is going to be equal to 50 degrees. Then we have angle Y. Angle Y is hitting that same exact arc. So we know the central angles are equal to the measure of the arc they hit. So angle Y right there is also 50 degrees. And now, since we know angle Y, that means angle X is going to be supplementary to that. So I would have to do 180 minus 50 and get 130 degrees for x. And that finishes that example up. Now we have our next example using our kind of first version of our last theorem. So we know we have kind of tangent points here and here, and this long arc they're showing us is 250 degrees right there. And that means that we have left over that blue arc, which would be looks like 110 degrees, so a little more than a quarter circle. And then lastly, to figure out x, we just need to do 1/2 of the difference between those two. And that means that we can do 250 minus 110 would be 140, giving us an answer for x of 70 degrees. Okay, now last example, we are told and shown that we have this arc on the left-hand side is 170 degrees, and we know that this angle on the outside is 50. So we just kind of use our formula there because we're trying to figure out the blue arc for x right here. So that work would look like we have an answer of 50 degrees, and that would be equal to 1/2 of 170 minus arc x. Because we're just using the formula, this would be the difference between the two arcs times 1/2 would be the angle. Well, now we just have the angle. So now we have basically to double both sides. We would have 100 would equal to 170 minus x. And we know that 170 minus 70 has to equal 100. So that means that 70 would end up being equal to our x value. And that wraps up part 1 of our video. Part 2 is probably the most straightforward of all these. When you have chords in a circle, they intersect at any point inside. The chords are divided proportionally. So this means that if you look at our first example on the left, A times B has to equal the same as C times D. So really easy stuff here. We're just, for example 1 here, we would just do 4 times x has to equal 3 times 8. Well, if this side equals 24, well, that means that 4 times 6 would have to make that work, making our x equal to 6. And in our second example, we would have x times 12 would be equal to 20 times 3. That means that we have 60, and we know that 5 times 12 is equal to 60, and that makes our answer for x 5. Okay, well, that wraps up part 2, and that was definitely the most straightforward of all of these. Moving to part 3, we have 2 versions of this same idea. Essentially, the secant version is that you have 2 secants intersect at a point exterior to a circle. The lengths of the secants and the external parts are proportional. So basically what we are saying is the whole secant line from this point on the outside right here, A, which is the whole length. If you A times the part just on the outside, and then C times the part on the outside, all of that's supposed to be equal to each other. And then you basically have the tangent secant version of that, where instead of one of your lines being a secant, it's just a tangent line instead. So you have A times itself, because you kind of have the same A here, the outside part and the whole thing are the same thing. And then you have B, the whole thing, times C. And you can see that our formula there, and then our other formula is similar to the one we just did over there, but with obviously the key difference of whole times part. let's do two examples of this theorem. So we have in example 1, 8, and then x, and then 12, and then 20. So this is the secant-secant one. So that means that for this one, we would have to do our left side. So we have to do the whole thing. This whole thing would be 8 plus x. And then the external part would just be 8. So we have 8 times the whole thing, 8 plus x. And then we have the whole thing on the bottom, would be 32 times 12 for the outside portion. So we have that right there for our setup. We know that the one side is just going to be 8 times both parts in the parentheses, but we've got to grab a calculator for the other part, giving us 384. So we would have 384 would then be equal to 64 plus 8x. Subtract 64 from both sides. We get that 8x is equal to 320, and we don't need a calculator for that. The answer would be 40 for x. Okay, now we have our last one here. So this is our tangent-secant theorem. So we're going to have 6 times itself. So we got 6 squared. And that is going to be equal to the b here, which is the whole thing. So we'd have x plus 5. So we have x plus 5 being multiplied by the external part, which in this case is x. So a little bit more challenging here. So we have x squared plus 5x is equal to 36. So we can subtract 36 from both sides to get a quadratic equation, and we'll use factoring to solve this. This would factor to x plus 9 and x minus 4 is equal to 0. And the two answers we would get would be negative 9 and 4. Well, negative 9 doesn't make any sense for the length of a segment, so we can cross out negative 9, and that means that our answer is just going to be the 4. And that finishes up part 3. That leads us to our last part and our final theorem that we're going to be learning about in this circles chapter in general. Our last theorem is what is known as the tangent chord angle theorem. So basically, you can see in the picture here, we have this point of tangency at B, and we have a tangent line coming away from it. But then we have a segment kind of starting from there, going towards the inside of the circle. So the important thing is that the 148 where they're showing in this picture is that red arc right there. And essentially it works the same as what we know about inscribed angles already, since this sort of is an inscribed angle, in that the angle itself is just going to be half of that red arc. So in the case of this example, the x would be 74 degrees. All right, so we have two examples here to walk through. They're both pretty different from each other. So let's try the one on the left first. So first of all, we have one arc over here that's y, and the rest of the circle, which we're going over in green here, is 3y, which means that we have y plus 3y equal to 360 degrees. So 4y equals 360, and y would be 90. So that shorter part of the arc is 90, making the longer part 3y equal to 270 degrees. Well, if we know that our x is hitting that green arc, we know that x has to equal 1/2 of that arc. And that means that our x value is 135 degrees. Our final example of the video is now up. So we have basically to figure out what angles A, B, and C are. And so A is easy to find because it's part of a straight line. So it would be supplementary with 50 and 45. So we can do 50 plus A plus 45 equals 180. If we take away 50 and 45 from 180, looks like that would be equal to 85 for our A value. So we've got one of our angles already. We can write in 85 right there. So now we need to find some of our arcs, because you can see how B hits this red arc right there, and then C hits our green arc right here. And we can see that those two tangent angles both hit those arcs. So this 45-degree angle hits the red one. So that angle would basically be doubling it to get to the arc. So that means that our red arc right there is 90 degrees. And we would double that green 50 degrees for the green arc. That would make that green arc equal to 100 degrees. So they're pretty close to each other. And then since B and C are both inscribed angles, they'd be half of that arc. So they end up being equal to the two angles we started with. So they would be 50 and 45 degrees, respectively. And that concludes our last part of this video and all of the new circle theorems and vocabulary we will need to be aware of in this chapter overall. Thank you for watching this video.